Suppose this block of steel is to have a recess cut along one edge. The job could be done by hand, but it's hard to hold the chisel in the correct position, and it's hard to keep the hammer blows uniform. One way to overcome these difficulties would be to mount the chisel on a power-driven shaft, with the work placed in a vise, so arranged that the work could be fed to the rotating chisel. But this arrangement is inefficient. Only one small chip is removed with each rotation of the chisel. Adding more chisels would be a further improvement. An even better arrangement would be to eliminate the shanks of the chisels, providing room for many more cutting edges. Now, with the teeth mounted in a wheel, or with teeth and wheel a single piece, chips could be removed much faster. Actually, there is a tool like this. It is called a milling cutter. The effective use of this tool requires a machine with certain basic features. There must be means for properly mounting the tool. There must be means for rotating it. The work must be supported. Here a vise is used. So that the work may be brought into position and fed to the cutter, means must be provided for moving it up or down, crosswise, and back or forth. To see how the cutter is held, let us begin with the shaft on which the cutter is mounted. This shaft is called the arbor. Observe the taper at one end and the internal thread. The arbor is inserted into the spindle. The spindle is hollow and has a tapered end to receive the arbor. On this machine, a drawbar is used. Its threaded end screws into the arbor. As the drawbar is tightened, it draws the arbor snugly into the tapered spindle nose. With the arbor tightly secured to the spindle, both will turn together without slipping. Now the arbor is ready to receive the cutter. But first, spacing collars are slipped on. Then the cutter. The collars provide means for setting the cutter at any desired place on the arbor. A nut secures the assembly. A sturdy overarm, having an outboard bearing, provides a rigid support for the outer end of the arbor. The overarm is secured by clamps. Now the arbor nut is brought up tight. Power to rotate the tool is transmitted from the motor to the spindle through cone pulleys, or through a combination of cone pulleys and gears. This cone pulley is linked to the spindle by a locking pin in the large gear, which is fastened to the spindle. Thus, the power transmitted to the cone pulley is carried by the locking pin to the spindle. Provision must be made for changing the spindle. As a general rule, the cutter should rotate slower for hard materials, faster for softer materials. Usually, slower spindle speeds are used with cutters of large diameters, faster speeds with cutters of smaller diameter. Guards over the driving mechanism protect the operator. On this milling machine, spindle speeds are changed by changing the belt connecting the spindle and countershaft, or by changing the belt connecting the motor and countershaft. Some work must be done at speeds slower than can be obtained with the cone pulleys alone. For these slower speeds, the back gears are employed. When the back gears are to be used, it is first necessary to disengage the cone pulley from the spindle by pulling out the pin. Then the back gears are brought into mesh. Now let's see how the work is held and how it is fed to the cutter. This type of work may be held in a vise. The vise is fastened to the table by bolts extending through T-slots in the tabletop. The table rides on a cross slide, which rests on a saddle. The saddle rides on the knee. Thus, the work may be moved in three directions. By means of the knee, the work may be raised or lowered. The cross slide moves the work crosswise. The table moves the work back or forth. To place the work in position to be fed to the cutter, it is raised alongside the cutter. Using the cross slide, the side of the work is brought into contact with the side of the cutter. Now the work is dropped just below the cutter. Then the cross slide is used to move it over the required distance. The distance can be measured on a calibrated collar. Or by using a steel rule. To review, the work is raised alongside the cutter. The side of the work is brought into contact with the side of the cutter, then dropped just below, and moved over the required distance. The next step is to set the work for depth of cut. To do this, the work is raised until it just touches the tool. Then it is moved away from the tool. Now the work is raised for the desired depth of the first cut. Usually several cuts are required to reach the specified depth. Remember, to set the work for the desired depth of cut, it is raised until it just touches the tool. Then moved away from under the tool, then raised for the desired depth of cut. The first cut can now be made. Here, the table is operated by hand to feed the work. When the first cut is completed, the work is brought back and raised for the second cut. The automatic table feed may be used to feed the work. A tripper is set to stop the table control at the end of the cut. That is, when the work has passed the cutter. The distance the work moves for each rotation of the cutter is called rate of feed. Feed must be adjusted to the kind of material, the depth of cut, and the diameter and speed of the cutter. Feed is controlled by turning the feed change knob until the desired rate appears. If the work is of hard steel, many cuts will be necessary to cut the recess to the required depth. If the work is of softer metal, deeper cuts can be made. In general, the wider the cut, the shallower each cut should be. The narrower the cut, the deeper each cut can be. However, the depth and width of cut, as well as the hardness of the work, must all be considered when selecting the diameter and speed of the cutter and the rate of table feed. In all cases, it is important that the work feed against the cutter. When fed this way, the cutter teeth bite into the work gradually, each bite starting at the bottom of the cut. This simple cut is just one of many that can be made on a milling machine. Through the use of special cutters, a wide variety of other milling operations is possible. In all milling operations, using the standard milling machine, the work is always fed along a straight line against a rotating cutter. The action of each cutter tooth is similar to that of a hand chisel. But vast improvement in accuracy and efficiency is achieved by the milling machine.